260 million years ago, this planet had one continent. One landmass running from the South Pole almost to the northern high latitudes. Everything else was water. A single ocean that wrapped the whole world and closed back on itself. We call the land Pangaea and the ocean Panthalassa. You could start walking from the ground that is now buried under Antarctic ice and end up on the ground that is now Siberia and never once reach a coast. There is no grass anywhere on this earth. Grasses will not show up for another 100 million years. No flowers either, and no dinosaurs. The first one is about 30 million years away, and the animals that will produce it are small and unremarkable right now. This is the Permian, the last stretch of the Paleozoic. It ends 252 million years ago in the largest extinction this planet has ever recorded. And almost everything I am about to show you goes with it. The Permian ran for roughly 47 million years. All of recorded human history, from the first written tablets to this sentence, covers about 5,000. Our entire written record fits inside this one period, something like 10,000 times over. This was not a moment in the planet's life. It was a long, stable setting. Pangaea took tens of millions of years to assemble, and the seams show. The Urals are one, the line where Siberia docked onto the rest of the land. Another chain ran through what is now Central Europe and continued into the Appalachians. Those ranges squeezed the rain out of the incoming air and left dry ground behind them. Through the summer, the interior heated up as one enormous slab. The air above it rose, and moist ocean air got dragged inland behind it. In winter, the whole system reversed and blew back out to sea. A monsoon at continental scale, and no landmass today is big enough to run one. It delivered most of its water to the coastal belt. The middle got a few violent storms a year, and then months of nothing. A piece of that interior is sitting in Arizona, and you can drive to it. The Coconino Sandstone is a fossil dune field turned to stone, in places close to 300 meters thick. In a road cut, you see long, sweeping lines inside the rock, all leaning the same way. Those are the faces of individual dunes, frozen mid-slide. Animals walked across those dunes. Their tracks survive on the slopes where the sand was damp, usually at night or near dawn, and you can read the mechanics off them. Small, four-legged animals climbing at an angle, sand collapsing backward under their weight, toes dragging on the downhill side. A person dropped into that country would notice the ground before the animals. No turf underfoot, because turf is a grass invention, and grass does not exist. The soil holds together on the roots of scattered shrubby plants and crumbles under a boot.
Dry air, almost no shade. The nearest water may be a day away. And the sound is wrong. No birds, wind and insects. The drought left more than dunes. Dig into the ancient soils and you find hard carbonate nodules that only form where evaporation beats rainfall, in rock that runs red from iron oxidizing in dry air. Oxygen isotopes in shells and soil carbonate give temperature. Growth rings in wood give seasonality, and the climate map of the period gets built from those pieces. Up in what is now Northern Europe, a shallow sea kept flooding a low basin and drying out again, leaving a layer of salt every cycle. Those layers stacked hundreds of meters thick, and they are still down there. Germany and Poland mine them, and engineers wash caverns into the salt to store natural gas. A Permian Sea is part of the European energy grid. Life on land tracked the water. Rivers came off the mountains, spread across low ground, left oxbows and swamps behind. Vegetation followed them in green corridors, and between those corridors, the country was open and dry. Now go south into the high latitudes of Gondwana, the block that later broke into Antarctica, Australia, India, Africa, and South America. Back then, it was one piece, sitting around the pole. There was forest down there. In the transantarctic mountains, geologists find petrified stumps still standing where they grew, roots in the ancient soil. The dominant tree was Glossopteris, a plant with broad, tongue-shaped leaves and a net of veins across them. Cut a fossil trunk, and the growth rings are sharp. A burst of fast growth, then a hard stop. Cold is not the main problem that close to a pole. Darkness is. The sun does not come up for months, and no amount of greenhouse warming fixes that. These forests handled it the way a larch handles Siberia today. Drop everything, shut down, wait for the light. Whole seasons of fallen leaves show up as thick mats in the rock, one autumn at a time. There was no permanent polar ice, and the tree line sat where a kilometer of ice sheet sits now.
Antarctica with forests is the kind of thing this channel exists for. If you want more versions of the Earth you would not recognize, subscribe, because the next one is nothing like this. Dimetrodon gets sold in dinosaur toy sets. It is not a dinosaur, and it is not really a reptile in the way you are picturing. It is a synapsid. And so are you. There is a single opening in the skull behind the eye, and that one hole splits the whole group away from the line that led to lizards, crocodiles, and birds. The big animals of the Permian belong to our side of that split. Dimetrodon is early Permian, about 3 meters long from what is now Texas and Oklahoma. The sail sat on tall spines coming off the vertebrae. What it was for stays open for a specific reason. The soft tissue never preserves, so nobody knows how much blood was moving through it. Heat exchange, display, structural stiffening, all still on the table. By the middle of the period, the Therapsids take over, and the skeleton shows why. Legs pulled in under the body instead of sprawling, teeth splitting into different shapes instead of a row of matching cones, heavier jaw muscles, a body built for covering ground and burning fuel. Most of the plant eaters were dicynodonts, and the heads are strange. Almost no teeth, a horny beak instead, and 2 tusks coming down from the upper jaw. The beak cropped tough stems, the tusks worked soil and pulled up roots. Rabbit-sized to ox-sized, and their fossils turn up on every continent we have. Some of them went underground. In the Karoo rocks of South Africa, there are spiral burrows corkscrewing a couple of meters down, and at the bottom of one, you will occasionally find the skeleton of the animal that dug it, curled where it settled. That is a reasonable response to a punishing dry season, and it tells you more about the climate than any temperature number I could give you. The whole system ran on a seasonal timetable. Wet season, the floodplains greened and herds spread out. Dry season, the water pulled back into a few holes in the riverbed and everything came to them. The animals drinking and the animals waiting on the ones drinking. Bone beds from those spots are chaotic. Whole communities jumbled into one layer. Not every big herbivore was on our branch. Scutosaurus was a pariasaur, a low barrel of an animal about 2.5 meters long, with knobs of bone on its skull and armor studding its flanks. Slow, heavy, and carrying an enormous gut for processing bad food. We know these animals largely because of one dig. In the late 1890s, a geologist named Vladimir Amelitsky found a bone-bearing lens in the riverbank of the Northern Dvina in northern Russia. He did not excavate specimens. He excavated the rock in blocks by the ton, crating it up over years of field seasons. Scutosaurus came out of that material, and so did the animal at the top of the northern food web. Innostrancevia, 3.5 meters long, skull around 60 centimeters, upper canines up to 15 centimeters. It was a gorgonopsian, and gorgonopsians gave the planet its first saber teeth, tens of millions of years before any cat existed. Judging by related forms, the skin was thick and bare, closer to a rhino than to anything furry. Front limbs stood wide, back limbs tucked under. Canines that long are a tool for large, thick-skinned prey. Get through the hide, hold on. In 2023, 2 specimens from the Karoo Basin in South Africa turned out to be Innostrancevia. Over 11,000 kilometers from the Russian sites, and nobody can say how they covered it. The timing is the interesting part. South Africa's own top predators drop out of the rock well before the main extinction, and the northern animals move into the empty slot. They did not last either. The big predators started failing first. Underneath all of that lived the animals nobody puts on a poster. Therocephalians and cynodonts, rat to dog sized, with differentiated teeth and a bony shelf separating the nose from the mouth. That shelf lets you breathe and chew at once, which means long food processing and a fast metabolism. Whether they had fur is unknown for a plain reason. There are no skin impressions from Permian cynodonts at all. This is the group that walks out the other side and eventually produces mammals. In the water sat the temnospondyls, big, flat-headed amphibians that lay on the bottom of a river and took whatever swam over. Some grew larger than a person. The really extreme size estimates come from fragmentary material, which is why cautious specialists keep revising them down. The sea was just as unfamiliar. Reefs were built by sponges, bryozoans, and calcareous algae instead of modern corals. The floor was carpeted with brachiopods, shelled animals that look like clams and are not, and crinoids stood in meadows on their stalks. Ammonoids and sharks worked the water above them. The last trilobites were still down there too, a group that had already been running for almost 300 million years. The decline starts before the main event. Roughly 8 million years out, marine groups thin and land communities reshuffle in what looks like a separate crisis. After that, the climate keeps drying, deserts widen, and the green river corridors carrying most of the land life get narrower every million years. The end came out of Siberia. 252 million years ago, eastern Siberia opened up. Basalt came out of fissures tens of kilometers long, sheet after sheet, for less than 1 million years. The volume of erupted and intruded rock is usually put near 3 million cubic kilometers, spread over something like 5 million square kilometers. Those figures carry real error bars. Much of the province is buried under the West Siberian Basin, and more of it has eroded away, so the number depends on how much you assume is missing. The lava was a regional problem. The gas was the global one. The magma pushed up through the Tunguska Basin, and that basin had coal seams, oil-bearing rock, and evaporite sitting in it. Hot intrusions cooked that material and drove off everything it had been storing for millions of years. Carbon dioxide, methane, sulfur, and chlorine compounds. You can see the result in the rock before you know the cause. At the boundary sections, the ratio of carbon isotopes swings sharply and then keeps wobbling, which is what a huge injection of light carbon into the air and ocean leaves behind. global temperatures rose on the order of 8 degrees or more. Tropical sea surface estimates run high enough that large marine animals could not shed body heat, and those numbers come from oxygen isotopes in conodont teeth in South China, which is why the exact figure depends on assumptions about ancient seawater chemistry. Warm water holds less oxygen. The ocean started suffocating from the bottom up. Low oxygen water spread onto the shelves, and a share of the carbon dioxide went into the water and moved its chemistry toward acid. Reef builders and anything with a heavy calcium carbonate skeleton were on the wrong end of all three of those at once. There is a case for damage above as well.
Pollen grains from the boundary interval show developmental defects, and one reading of that is ozone loss from all the volcanic chlorine. Other readings exist, and the argument is live, but the malformed pollen sits in the rock regardless of who wins it. The size of the loss depends on how you count, so take a range. Older estimates put it as high as 96% of marine species. A more careful recount that strips out ordinary background extinction lands near 81%. On land, roughly 70% of vertebrate genera. It is also the only mass extinction that hit insects hard. Reefs vanish from the record for millions of years afterward. The brachiopod carpets thin out to scatters of small shells. Crinoids squeak through in a few lines, and the trilobites end. Walk a lower Triassic marine section, and the fossils get monotonous in a way that is hard to describe until you have seen a Permian one. On land, you can measure it without fossils at all. For the first 10 million years of the Triassic, the planet lays down no coal whatsoever. The rivers change shape too. Meandering channels need plant roots to hold a bank in place, and they get replaced by wide braided flows dumping sand across open ground. Atmospheric models add one contested detail. Several reconstructions have oxygen falling through the end of the Permian and into the Triassic. Nobody can measure that directly, and the models disagree. But if it happened, breathing at altitude became hard work, and stretches of high ground turned into barriers animals could not cross. What is left looks empty. In the lower Triassic beds of the Karoo, one genus accounts for most of the land vertebrate skeletons anyone finds. Lystrosaurus, a pig-sized dicynodont with a barrel body and a pair of tusks. It inherited a planet because almost nothing was left to compete with it. Diversity took millions of years to rebuild and came back rearranged. The group that rose had spent the entire Permian in the background. Archosaurs, the branch holding crocodiles and the future dinosaurs. First dinosaurs, about 20 million years after the boundary. Therapsids survived, but the big roles were closed to them. The cynodonts got small, stayed small for 150 million years, and only got another shot when the next catastrophe cleared the field. You can put a finger across the line between the two worlds. At the Meishan section in southern China, the interval where the fauna changes is a matter of centimeters, including a thin clay bed that marks the moment. Below it, a Paleozoic ocean with all its architecture. Above it, near empty water. The Siberian basalts are still sitting there. Metals came up with that magma, and the ore bodies at Norilsk are a direct inheritance from it. Nickel out of those deposits goes into stainless steel, palladium goes into electronics and exhaust systems. The event that ended the Permian world is currently being mined, refined, and traded on commodity exchanges. Tell me in the comments which piece of this you want as its own episode. The polar forests of Gondwana or the hunting grounds of the gorgonopsians. Whichever gets more votes gets made. And subscribe, because the next lost world is already picked out.